Welcome again to this video that is solving exercise 5. Up to now we have input our data, which is the hourly series in a gauge in Oviedo, and then we have created the series of annual maximum for several stored durations like these ones, 1, 2, 4, 8, 16 and 24 hours. So we created this table. The next step, which is the third in the exercise, is to feed a GEV, which is a general stream values distribution, to the series of annual maxima. Okay, I'm gonna go to the complete exercise to show you what's a GEV. So remember, in the previous video we learned how to feed a normal distribution. A normal distribution has a PDF, so this is the PDF, that is like a bell, and the regular normal distribution or standard normal distribution is centered at 0 and it's symmetric, so it has values like this. So a GEV is a special distribution created for stream values, which is what we're working here with. So stream values of precipitation, and it has a PDF with a shape like this. So depending on the parameters that we feed, it will take a more pointy shape or more elongated shape. And if we integrate the PDF, we get to the CDF, which is like this. Okay, we are gonna follow the same steps that we did in the previous video, in which I told you how to use the normal distribution. The only difference is that instead of stats norm, we're gonna use starts gen extreme. Okay, good. So first of all, we need to import from SciPy stats, which is the statistical tools in SciPy. We're going to import the GEV distribution, which is called gen extreme. And apart from that, we're going to import another tool, which is called stats models, distributions, empirical distribution. And from here, we're going to import the empirical cumulative distribution function. We're going to use this just to check visually how our data, how our fit is if it's good enough or not. So I'm going to start by doing an example as before for the 2 hour storm. Okay, let's start by visualizing the data. We have already did that before. So seaborn, this plot, and we put the annual max for a duration of 2 hours. Let's say the bins to 8, and let's feed a gen extreme, so a GEV distribution, semicolon, and this is our the histogram of our data. The blue line is the kernel density estimator. Remember, it's just a way that has this plot to show us more or less what's the shape of our function. And then the black line is the fitted gen extreme values for this histogram. So now we're gonna get the parameters of this black line. So feed a GEV. Okay, how do we feed this? The basics are just the same as what we did with the normal distribution. So we call function gen extreme and we apply the fit. We input data, annual max for 2 hours. And in this case, 1 second, I'm gonna go to the complete exercise. The GEV is a mixture of 3 different functions, which are the Gumbel, the Bible, or the Frechet distribution, depending on the parameters. If we fix the first of the 3 parameters to 0, we're using a Gumbel distribution. So this is what we're gonna do. So the first parameter, we're gonna fix it to 0. So from the 3 types of GEV distributions, we're gonna get to the first type, which is the Gumbel. And then we get the 3 parameters fitted. So we fix the first parameter to 0 with this attribute here. That's why this is 0. And then we get the other 2 parameters. Let's save these values as parameters of the GEV for the 2 hour storm. And still we can plot it like this. And then we're gonna feed the empirical distribution, for which we imported this function here, ECDF. So the ECDF, the empirical CDF for 2 hours will be we'll just apply the function to our data, maximum 2, and that's fitted. And now let's plot what's our fit. So let's create values of intensity with the linear space, lin space. The start is going to be 0. So far there's no negative precipitation. And the end, let's call it something like 25, for instance. I'm going to create 100 values there. So now let's plot the CDF for these I values. We get into the function gene extreme. Okay, we can define our parameters with this function here. So we need to define 3 parameters. With this asterisk, we're telling the function that in this object are contained the 3 parameters. So we don't need to import parameter 1, comma, parameter 2, parameter 3, but we just put them all together with one object, which is pargv to h. Okay. And then we apply a function to this, which is the CDF, and we apply the CDF to our I data. With this, we have created the CDF. Good. And now we want to see the empirical distribution that we have fitted here. So PLT plot, and then for annual max 2, we apply the ECDF to H for our annual max 2. And let's plot it as dots. Oh, sorry. I'm mixing this here and here. Good. We put here a comma, and then, so the blue line is our fit, and the orange dots is the empirical distribution. The empirical distribution, it simply divides 1 by the number of data we have. So we have 14 values. So basically it just divides, it sorts of all the values in the annual maximum series, and it gives probability of 1 to the maximum, and then 13 divided by 14 to the second value, 12 divided by 14 to the third value, etc., etc. Okay, so it's just a way to see if our fit is good enough, and it looks like it is. So now this was an example just for 2 hour storm. We have to loop this process for all the storm durations. So loop for all storm durations. Okay. As we did before, we're gonna create a table or a data frame in pandas terminology, in which we're gonna save our fitted parameters. So pandas data frame, and we create the index is going to be the name of the parameters, which is xi, mu, and sigma, and in the columns we're gonna input the durations. Okay, so this is an empty table with the name of the parameters and the duration. So now we're gonna do a loop for each duration. We're gonna fit or fill in these 3 values for the parameters. How do we do that? So for d, or lowercase d in duration, okay, we're just gonna go up here and copy this. Okay, so we're gonna get into the gen extreme and fit it for the series for that duration. We always fix the first parameter to 0, so we're fitting on Goomba distribution, and we save these values in our table parameters for the duration column. Now our table looks like this. Okay, so now we have all our parameters fitted for every storm duration. See that the first row is always 0 because we have fixed here the first parameter to 0 to fit a Gumbel distribution. And let's visualize this fit. So we can copy this plot here. Okay, and let's increase this a little bit. So for instance, up to 35. And now I created here another loop. So for every duration, we're going to plot the gen extreme for, we have to get here into parameters of that duration and y. Okay, let's comment this now. Okay, so these will be the GB CDF for each of the storm duration, and we can add to this the empirical distribution. To do that, we're gonna do something like this. So D, and now we have to skip this. Basically, we're gonna call the eCDF function, apply the annual max 2 times. Okay. Let's give it a label so we can plot a legend afterwards. This is gonna be str is to create a string, so D is an integer which will take values like 1, 2, 4, 8. With this we're gonna create it as a string, and we're gonna add another string which is hours, and you'll see now why we are doing this. Now we can create a legend. To create a legend is just plt legend and semicolon in the end. Okay, let's do it something different. Scatter instead of plot. Okay, and we give the size of the dots with the S. Good. So now this looks better. So we have our the distribution for 1 hour precipitation, or 1 hour storm. Sorry, the distribution for 2 hour storm, 4 hours, etc., etc., etc. Okay. We should check that the points more or less follow the fitted line. That's not totally the case for 1 hour precipitation, but it is for the rest of the storm duration. So right up to now we have finished the third step in our empirical in 1 hour exercise. I'm going to follow with the empirical IDF, which is the fourth step. So empirical IDF. Good. I'm going to go for a while to the complete exercise. So we have done all of this, and empirical ADF. There's a connection between the non-exceedance probability and the return period. So we want to calculate our IDF curve for some return periods, and we have a CDF in which we are using the non-exceedance probability. So the way to connect non-exceedance probability, which is the CDF, with the return period, which is the R, is this formula here. So if we want to calculate the non-exceedance probability of a return period of 10, for instance, this will be 1 minus 1 divided by 10. It means a non-exceedance probability of 0.9. So we have to get into the CDF curve with a probability of 0.9. Okay, so this is important. Let's go back to our exercise. As always, I'm going to start with an example, and then we are going to look it for more complex stuff. So we're going to work again with the 2 hour storm and a 10-year return period. Okay, so let's set duration and return period. So D will be 2 for duration, and TR will be 10 return period. Following this equation here, we can calculate the non-exceedance probability. non-exceedance probability. It's 1 minus 1 divided by return period. So as I told you before, for a return period of 10, the non-exceedance probability is 0.9. This means that we can get into the CDF curve at 0.9, and if we create here an horizontal line, all intersections with these lines here, now we're working with 2 hours, so let's go to the horizontal line up to here. We can extract the value of intensity for a return period of 10 and a storm duration of 2. Okay, basically we're doing this. Getting to 0.9 here, horizontal line up to the CDF for 2 hours, and extract the value of intensity. How do we do that? This is the PPF function that we saw in the basics statistics. So gen extreme, we define the parameters. So we have a table with the parameters, and we're working with a 2-hour storm. So we define the parameters for 2-hour storm, and then we apply the function PPF with a non-exceedance probability of 0.9. And this is with S parameters. And we get a value of intensity of 14.15. So the value that we did here, 0.9 here, and then down is 14.14. Okay, let's save this as intensity for 2-hour storm and 10-year return period. Okay, and we can visualize the fit. So what we've done is, let's create again a NumPy linspace that starts at 0, stops at 20, and we create 100 values, and we're gonna plot I against the gen extreme for parameters for the 2-hour duration, and then so this is simply the CDF, and then we're gonna create horizontal lines. So what we did was we created an horizontal line at the value of 0.9, which is non-exceedance probability, and then just put it like this. So this means that it will start at 0 and ends at 20. And let's give it a line style with dotted line. Okay, so we created this horizontal line at 0.9, calculate the intersection with the CDF, and then created a vertical line. We can, so that vertical line is at value yi to h 10. Let's say that it starts at 0 and it ends at 1, and again we give a line style of dotted line, and this is how we got our 14.5, almost 15 intensity. Good. If this is understood, we can continue by doing this for every duration, every storm duration, and return period. Okay, first of all we have to define return periods. Return periods. Okay, we're going to work with the following return periods, not really large. So 2 years, 10 years, and 30 years. And let's save this as a floating point array. Okay, so R is this S is okay. So why I'm working with these short return periods? Because our series has only 14 years. So there's a rule of thumb that says that you cannot work with return periods larger than 3 times the duration of your series. So in our case, the maximum return period that we can estimate is 45 years, but I'm just gonna keep it to these simple values, 2, 10, and 30. You can add as many return periods here as you want, and you will get more lines in this plot. Okay, so we're only gonna get 3 lines for 2, 10, and 30 year return period. So now, what's the non-exceedance probability for this return period? Is the same equation we did before, 1 minus 1 divided by r, and we have non-exceedance probability of 0.5 for the 2-year return period, 0.9 for the 10-year, and 0.96666 for the 30-year return period. Good. And now we have to calculate the rainfall intensity for each duration and return period. Let's do it again for intensity, for duration 2 hours, all return periods. We can do something like this. So now we'll call it just intensity for the 2-hour storm duration, and again we call gen stream. We set the parameters, which are in table parameters for 2 hour, and then we call the ppf, but now we're gonna call it to an array with 3 values. Okay, so we're gonna get, instead of just 1 value, 3 values. So this will be the intensity for a return period of 2, this will be the intensity for a return period of 10, and this will be the intensity for a return period of 30 years, sorry. So let's repeat this for all the durations. Let's create a data frame for the IDF empirical. We call it IDF E, and we create a data frame in which the index is going to be the return period and the columns is going to be the duration. So IDF is this, okay? Duration and return period. And we have to fill in this table. Let's do one more thing first. So we give a name to the index, which is return period. And now we're gonna do a loop for every duration in uppercase D. We're going to repeat this process here. So for every duration, we get into the parameters of that duration, and we save it there. And now if we print the table, I did a mistake. Oh, we get values of intensity for durations of 1 hour, for 2, 10, and 30 year return period, 2 hours, the same. Okay, we can check that these 3 values here are these 3 here. So now we have all these points to create our empirical density function. First of all, let's save the results. Save results. So we can just save our data frame as a CSV file, and we have to set with this the file that we want to create. So 2 dots to go 1 folder up. I just repeat the process. We are here. 2 dots goes to the precipitation. Sorry, we are here. So 2 dots goes to the precipitation folder. Then we're gonna go into the output folder, output, and save it as exercise 5 results empirical idf.csv. And we can set the format of the numbers that we want to save, and with this we are creating just 1 decimal point values. Okay, so now we have here exercise 5 results empirical CDF, and this is a table for every return period and duration. We have the intensity. Okay, and now we can plot empirical IDF. Plot empirical IDF. First of all, we're gonna define the size of the figure. Let's give it a size like this. Okay. This plot is a little bit complicated, so we'll go step by step. First, we're gonna set a title, which we're gonna call it empirical IDF. We can give it a type of font, which is given by weight, and we call it bold. Okay, so now we have a table with the empirical IDF. Let's give the X label, which is duration. Okay, now I have duration here, and the Y label, which is intensity in millimeters per hour. Okay, and then we have we're going to set a limit to the y-axis here, which is intensity, PLT, y limit. This is going to be a minimum of 0 and a maximum of 25. Okay, so we have a plot like this, and then we're going to define some colors for every return period. So let's say these are just colors. You can just put blue, green, red, but just to make it a little bit nicer, I'm just putting these colors here. And okay. And now we're gonna do a loop for every return period. So from TR for every return period in R. What is this enumerate doing? It's giving me both the position or the count in the loop and the value inside R. So if we get into R, we have 3 values. Okay, the first time I get into the loop, it will give me a 0 because it's the first time we get into the loop. That will be the I, and then the value of R, which is 2. Okay, if I put just print ITR, we see that the first time we get into the loop, it gives us, this is the count 0, and the value of R is 2. Second time into the loop, it's count 1, and it gives us the second value here, etc., etc. Okay. And now we plot a scatter plot with our duration and the IDFE. We get into our table with results for this return period. Basically, I'm just gonna give here some attributes like the color. That's why we wanted the I. So the first time we're gonna plot it in color tan, second time color dark khaki, etc., etc. And then the size of the dots, let's give it a 10. And then let's plot it some labels to understand what's in everything. So remember that a string creates a string out of numeric values. Int is to create an integer. Okay. Okay, so now you see that we have the points in this table. These are 3 by 18 points, and we have plotted here 18 points. If we plot the legend, this could be easier. So fig legend, we plot the legend. Okay, here. So it means that the brownish color represents the 2-year return period. The green color represents the 10-year return period, and the darker green color is the 30-year return period. We can make this a little bit nicer by setting the location of the legend and the number of columns. So now it's here and it's a little bit nicer. If we want to save the plots, we just say put PLT save figure. We have to specify the output file, so we're gonna call it exercise 5 empirical IDF, and we save it as a PNG file, and then we set the resolution, which is 300 dots per inch, and we have saved an image here which is called the empirical IDFs. Okay, it's better if we watch it from here. So exercise 5 empirical IDF, we get the figure like this. We're still not done with the exercise. We have done 4 out of 5 steps. This is empirical IDF. I'm gonna stop the video now, but in the following part, we have to feed an analytical expression to these dots here. So we get a soft line like these ones.